Bismillahirrahmanirrahim. Assalamualaikum. Good afternoon to all. Today we will continue from the class on Tuesday, which is on performance criteria and controller tuning. And we will go today more towards the controller tuning. We finished the one on the performance criteria. And now today we'll go more on the controller tuning. We have seen the different response using the P, PI, and so on. We have seen the different types of criteria and aspect that we have to look in performance criteria. We have seen the qualitative, quantitative, steady state criteria, the dynamic criteria at certain times, and the full length. The different types of criteria, and what are they, and what are the advantage of this criteria. These are all we can see, most of it in the chapter 18 of the book. And some parts of the controller tuning can be seen at the end of chapter 16 on the frequency response, but there is a section on Ziegler-Nichols and a little bit on the comparison with other tuning. So on the controller tuning, basically we have two well-known controller tuning methods. There are many methods, a variant of this method and other different methods now we can find in the market, but these are the most popular, the most basic fundamental methods. One's a closed loop method, the Ziegler-Nichols method, based on ultimate gain, crossover frequency, something we should mention later in the frequency response issue, which is equivalent to knowing one point of the open loop frequency response diagram. So this is a closed loop method because it is you tune it while you are closing the loop. Although this is a old method, it was basically developed in 1940s, but it's still the most popular one being used in the industry, see, for initial controller tuning. So it's not outdated at all, as some people said in the lab report. I saw that some people said Ziegler-Nichols is outdated. It's not outdated. It's still being used. It's still for popular. It's still well known for initial tuning of controllers. The other method is the open loop method, which is also called the Cohen-Good method. It came a bit later in 1950s. Still being used partly in the industry, but not as popular as Ziegler-Nichols, but it's open loop. This method requires the use of an open loop step response, what we call process reaction curve. So it's more. So this is more an open loop where you open up the controller loop. Method basically is as I said, a closed loop procedure. And what you have to do here, I think some of you may have done it in your labs when you did the method of comparing these tuning methods with the trial and error method. So one of them in the lab is to try using the clinical method. So you may be quite familiar with that. That is online testing you did online in the real plant. This one you are doing it in the classroom simulation, basically. Okay. The first thing you do is just to turn the controller, tune the controller to the P only mode. Okay, you can say use the P mode only and turn both the integral and derivative modes off. Okay, you don't use the integral and derivative mode, just use the P controller, and then you increase the controller gain slowly until the loop starts to oscillate. Okay, so when you get it slowly, you increase it slowly, you should be getting the loop to slowly starts to oscillate, oscillate until you get continuous oscillation for the response. This is an example to show you when you have the different types of oscillation. You increase your KC, until you get some sort of a continuous oscillation going through here. And from here you get what you want. Basically the two basic parameters that you need, the KU ultimate and the ultimate period here. You need ultimate period. So once you have the KU, the one that gives you the continuous oscillation, okay, until oscillation, and then you get your ultimate period. This is being used to tune the controller. Okay, of course you put it as a certain set point change. increase a set point change, or you can also use for disturbance rejection case, but normally you try for a set point change and try to get this oscillation. And once you get the KU, the ultimate gain that gives oscillation, and the ultimate the tuning P tuning or KC tuning that gives oscillation, the KU, or the ultimate period here. And so you can calculate from here to here. Okay, calculate from here to here. At different point, but this is the easiest to see. Then start to use these values, the ultimate gain and the ultimate period, and feed it into this uh, controller settings set up by Ziegler-Nichols. If you have just P controller, you can just use the formula here, 0.5 of KU. If you want to design the PI controller, then you can use this 0.45 KU, or you can use the PU over 1.2 period or 1.2. If you are going to use the PID controller, then you can use this formula, 0.6 KCU, PU over 2, and PU over 8. So it depends on which controller you want. This is the formulas that you need to use. Okay, and I think, as I said, you may have done it in your lab. You could have seen this. Okay, in your lab you may be dealing with proportional band instead of KU. It's just the inverse. You know, KC equals 100 over proportional band. It's just an inverse of the formulas, but the way, the methodology is still the same. And so you can get your tuning constant using the Ziegler-Nichols, and this is basically based on a theoretical basis on experimentation done by Ziegler-Nichols to come up with tuning. It's popular method. It may not be the best at the end, but this will give initial settings for your controller tuning. Later on, you can fine tune. So this is the advantage of having all this controller setting, is that they give you an initial value you can use to start off for your controlling, not just at random from any point you want. As you can see in your lab, you may have used it from different values, but it still had some systematic way of changing your settings and so on. That's fine, but that takes a lot of time. This one will give you initial setting you can start off with, and then from there you can do your fine tuning to get your better controller. So this is a closed loop system, because you are running the controller on closed loop. When the P controller is hooked up to the system, and you see how the response is. So this is control closed loop method. The next one is the open loop method, which is called the Cohen-Kuhn method. And open loop, why? We'll see later. So how's the method? The Cohen-Kuhn method can be summarized as follows. After the process reaches steady state at the normal level of operation, introduce a small step change in the controller output that goes to the valve and record the transient, which is the process reaction curve. So you do a step change in the controller output to the valve. You basically break the loop, make it manual, and you step change here. You can say, so you put a step change. You need step change, or in this case, a step change is magnitude M. So M over S instead of 1 over S. You introduce a step change to the valve. There's no disturbance, of course. You don't use any set point change in it at the moment. You introduce into the valve, into the system response. And you record the changes. What you expect to find most of the time, not all of the time, most of the time you expect to get a process reaction curve or curve. And from the axial model curve, you can get certain parameters. So when you get the curve, the process reaction curve, you draw a straight line tangent to the curve at the point of inflection, shown in the figure, and the intersection of the tangent with the x-axis, time axis, is the transport lag TD, and the first order constant T can be obtained from your BU, the final value that you get over the slope of the response. Okay, you can see here, this is you did just now the open loop test. You're supposed to get the response here from the measurement recorder. So normally you should get a process reaction curve response, a sigmoidal sort of response. So what you do, you get a tangent at the inflection point, draw a tangent there as much as possible, as close as possible. Slight difference may not be not big issue. And when the tangent line crosses the x-axis, which is the time axis, then that is your TD value, delay time. And to get your T, which is your time constant, is just the BU. BU is the final value that the response goes to after you introduce the step change to the valve, and you divide it by the slope. This is the opposite, slope equals this one. But right, to get T, you get BU, and you get the slope. Divide BU over S, you get the T, and you're going to use it later into your controller setting formula. So you get the T, you get the TD, where BU is, as I said, just an ultimate value at the final time, and as is the slope of the tangent line, you divide the inflection point as much as possible. You can find the inflection point where the gradient suddenly changes, and the steady state gain that you want to use can be given from Kp equals to the final value gain divided by the step change that you the magnitude of the step change that you introduce, the M here. It could be unit, it could be M. Okay, but normally it's just a certain value M. So when you get that value, okay, BU over M is your Kp value that you're going to use to put into your formula to get the tuning of the. So once you have those formulas, the Kp, T, and TD from the step 2 and step 3 just now, you have your TD values, you have your T values, and your Kp. So you feed it again into this controller setting, what you call parameter equation that has been developed by Cohen-Kuhn. Another again from trial and errors that they've done through the experimentation in the industries, in their instrumentation company, if I'm not mistaken, Foxper. They've done a lot of testing and training and on their systems, and they found, okay, for P controller, this is the equation you can use to get your Kc value. For Pi, this is the equation. For Pd, this is the equation. For Pid, this is the equation. Of course, there's slight difference here and there in the equation, just like Ziegler-Nichols, but this is basically what we call the Cohen-Kuhn controller settings. So basically, two basic conventional methods: the open loop method, the closed loop method of Ziegler-Nichols, and this open loop method of Cohen-Kuhn to get up to your controller settings that you can use, basically theoretically or in simulation, not just trial and error or randomly, to find the best controller for your system. Okay, of course, for most of them, you need to have that condition. For Ziegler-Nichols, you need to get that continuous oscillation. Okay, most of the time you get, sometimes it will be quite difficult to get as much as possible. Also, the Cohen-Kuhn, you need to find you get to get the sigmoidal reaction, process reaction curve response. Most of the time you get, but not all the time. Some systems are fast, may be difficult. Most of the time we noticed last time sigmoidal systems that are slow, multi-capacity systems. But according to what they found out, most of the system behave like that when you run the system as designed. So these are the basic two controller settings that we can use. Of course, we don't have to memorize this. Normally should be given to you. The Ziegler-Nichols setting can be given, it can be easily memorized, not a big issue for the one, but this one is more complicated. So it has to be given to you. You can use it and feed it into. And look, the next one we say the example, Cohen-Kuhn and Ziegler-Nichols, if you have this system, multi-capacity system, which definitely will give process reaction curve. So you do this, all the steps that you need to do, draw the slope at the inflection point, get the slope, what's the ultimate response in this case is 1. You introduce a unit step change, so the M is 1. So if M is 1, so the gain, the ultimate response is 1. The magnitude step change is 1, so it's 1, K is 1. Effective time constant you get from the final value 1 divided by the slope, which is 1 over 0.05, which is 20. The date time you get from the where it cuts the x-axis, 2.5. So these are the values you're going to fit into the controller setting. And what does it mean? Also, that what it means is that those values gives an approximate reaction curve, which is given by this. A reaction curve is given by a first order system with date time with delay. So delay is E minus 2 minus TDS, and the K is 1 divided by tau S plus 1. Tau is given by 20, so 20. So this is sort of the approximate equation for the curve that you get when you use the Cohen-Kuhn method settings. This is a sort of equation you get, and then you can compare next with the real curve, and you can compare. So this is from that equation. This is the approximate response that you got, and final response you get. So a little bit way off, but roughly this is just enough to get your controller settings, which is the most important thing. So using the Cohen-Kuhn method, uh, you can decide if you have your proportional controller, this is going to be your KC. If I use the PI controller, this is going to be KC and tau I, depending on the formula you use. If you use PID, this is going to be KC, tau I, and tau D. So you can see different KCs, different tau I, tau D when you use different types of controller and different systems. So there's no specific standard controller settings for different types of controller and so on. So this is the Cohen-Kuhn example of using the Cohen-Kuhn method. This is the controller settings you are going to get. Use the okay, just look through again. When you have Cohen-Kuhn, what does it show? You show for set point changes, and for disturbance, you get roughly this sort of response. If you use the Cohen-Kuhn settings, you get this sort of response. For disturbance changes, it's giving you about decay ratio 1/4 to 1.3, or this 1.3, which is reasonable. So it shows the closed loop response with foregoing settings for the set point and load changes, right? And we notice that if the Cohen-Kuhn setting produces underdamped behavior with rather good decay ratio, so far acceptable, not the best, acceptable. I said normally this is being used for initial settings, initial trial, or the initial values for control setting, and then you fine tune it further to get better results, as you have done also in your lab case. So this is the Cohen-Kuhn sort of response. If you just use Cohen-Kuhn straightforward without any fine tuning, this is the sort of response that you get. Not the best, but reasonable. If you use the Ziegler-Nichols method on the same system, just not the multi-capacity system, and get the continuous oscillation, you're going to get the KU for 12.6. Ultimate period, you will get about 15.14 minutes. Either you can calculate using a formula or use the frequency response technique. Later they will show you. Or what you can get again straight from the graph, you can get 15.14. And if you implement into the control Ziegler-Nichols, normally we call it the ZN settings, you get for the proportional controller is divided by 2, K is 6.3, for PI is divided by 2.2, you got 5.7, the PU divided by 1.2, you get a 12.62 for tau I. For using PID controller, you get a KC divided by 1.7, which is 7.4. Tau I, which is divided by 14, divided by 2, you get 7.7, and tau D equals to 1.89. So you will see that the different values KC and tau I for this example. And let's see then, just to compare the two results, the proportional gains are a little larger for the CC settings, but the reset and the wait time. Reset and wait time means this is the tau I and the tau D are higher for the ZN. So that's the normal. This is not general. In this case, that's the case. And if you compare their result, this is the result that you will get. Indicate the response of the closed loop system to step changes, set point, and load using PID controllers with Ziegler-Nichols and Cohen-Kuhn setting. We notice that the response with ZN tuning are slightly better than those with the CC settings. Must be emphasized though that no general conclusion can be drawn as to the relative superiority of one method over the other. The only conclusion we draw is that both methods provide very good first guesses. Remember, first guesses for the values of the controller's adjustable parameters. So this will give you a reasonable comparison. You cannot make any general conclusion, but roughly you can say Ziegler-Nichols is better. But that's by visual qualitative what you call criteria. If you want, you can use the quantitative criteria, and as you will see later, and then we can compare them exactly which one is better in which criteria. But roughly it looks like Ziegler is slightly better, faster, lower or faster response back to the set point. The lower overshoot, okay, slightly lower, also not so much different. Response time is the same, slightly less overshoot again, more or less about equal in terms of oscillation, but maybe faster in decay, and then finally response was slightly better, but not you can say generally both are acceptable. And again, these are only first guesses. What does it mean? This is only the first initial setting. You can fine tune it later to get it a much better result, what you would like. So it's just to show that both of them are reasonable methods for initial controller settings. You can use them, and you can what you call tune real life system controllers using these methods once they're applicable, and then you can fine tune to get better tuning and so on. So this is an example of how to use these two methods for the multi-capacity case system. Another example you can see from the book is given by in terms of this equation, in terms of the system, also a multi-capacity system, S plus 1, 4, it's a slow system. Okay, and in this case we want to again determine the controller setting, okay, for this PI controller, in this case the PI controller. Okay, so we apply the ZN method for PI controller, we obtain the KCU4 and PU2 pi, and then you want to get is KC equals 1.8 and tau equals 5.3 using the Ziegler-Niggles method or the equations. If you use the Cohen-Kuhn method also, it's possible for this sort of system. It's a multi-capacity, definitely will give you a process reaction, sigmoidal shape can be applicable to using Cohen-Kuhn immediately without having to check anymore. But to get those values for Cohen-Kuhn, you can use two methods. One, you can use the reaction curve method, they call here CC1. What you do is you do a little bit of equation settings, equation manipulation of the equation to get the final response CT, and then from that you can find the inflection point, okay, where the differential, by the differential, you know that at inflection point where the gradient suddenly changes, the second order derivative is 0. So you can solve that, and from that point you can solve your slope. Okay, you can solve at what time does the inflection point happen at 3 t equals to 3, used to fit into the gradient, and you get the slope at that point, and that's your S. So you can use the calculation method, what you call using the reaction curve method. That's what has been proposed in this method. To get inflection point, you can get your slope, you can get the point where it cuts the x-axis time axis, that's your TD, and you can get your K, the final value divided by the unit step change. In this case, if you put unit, then it's a unit. So BU divided by KU is just 1. You can get all the values to get the controller settings using this method. Or you can curve fit this. Once you got try a curve fitting method. Fit it with the equation that we're supposed to fit the sigmoidal or response curve method, which is first order with delay time. So you fit it. Okay, this is the method that is get the inflection point. Okay, and this is how you get your S and so on from here, and your TD equals to 1.42, S equals 0.224, and so on. And your final value in this case is BU is 1. Your time constant is BU is 1, final value is 1, and S is 0.224, so your time constant is 4.46. Okay. To use a second method, you can curve fit the value using softwares. You can use the loop software and so on. Try to curve fit the response that you get into this equation that is supposed to be the first order with delay time. That's supposed to follow the sigmoidal shape. Normally this curve, this equation will give you the sigmoidal shape because you got a delay and you got roughly it's a first order system. So using this, you try to fit it and you will get the time constant 2.65, the date time 1.79, the gain 1.03. The fit is about 0.9972, and squared average point is good enough for us to use. So either way you can use that, either curve fitting method or the first response curve, and use from there you can get your contour, the Cohen-Kuhn settings using these two methods of getting the TD, tau, and KP value. And this one shows the values that you get if you use your Ziegler Nichols method, or your KC and tau you get. You use the Cohen-Kuhn method, the two methods. You got the first method, percent reaction curve. You get this for your KC and tau I. This is for PI controller. If you use your loop flow method, you get your KC and tau I equals to 1.374 to 548. Okay, and using these two methods, you run the response, set point change, or in this case the disturbance. In this case, it's disturbance rejection, keep set point fixed. So you calculate what is going to be you calculate the dynamic criteria, ITE, ISE, ISE for Ziegler-Nichols method. For Cohen-Kuhn method 1, you calculate the ITE, IAE, ISE. For the Cohen-Kuhn method 2, you calculate the ITE, IAE, ISE. And then you have the same thing that it calculate the ITE, but you can solve, as I said last on Tuesday. Somebody asked me the question. If you do not tune it, then if you use the ITAE, IE methods or IC method, you can minimize that value and to find what are the parameter tunings that will minimize those values. So if you use a minimum ITAE criteria, these are the values it will give you for the minimization. KC 1.18, tau I 3.28. And these are the minimum ITE that you're going to get for using that method. And you can calculate the ISC, IE as well. You use the minimum IE criteria. This is the KC values it will give, tau I values it will give. And this, of course, this is going to give you the minimum IE from all of them. It will give you definitely the minimum. And the ITE, IC can also be calculated. If you use the minimum IC values, these are KC, tau I values it will give. And consequently, you're going to get you can calculate the ITE and IE and ISC, which is supposed to be minimum. Because you minimize it, so it has to be the minimum of all the different values here. So this is supposed to give you the best. So you can use these criteria for all three criteria. You can calculate for the different method. Minimum IT, you can calculate their values. You can calculate their values, and minimum IE, you can calculate their values to see what is their value. But at the end, you can compare the KC and tau I. Slightly different here and there, but the values of ITE can be quite big. In this case, the CC1 method gives an ITE big, which means there's something going wrong when you go for a longer time. The response not be too good. It's going to be very big ITE with respect to time. If you don't use the time, it's not so big, but it's still big, showing that it's not so reasonable in terms of this using this method. And the others are quite small, and of course this gives you the smallest response, smallest values for these three cases. And you can see from here, if you just compare the Ziegler-Nichols and Cohen-Kuhn, you can find that the Cohen-Kuhn method just now, we saw the ITE very high, so it just looks like it's not going to be stable, increasing and increasing and increasing. The Cohen-Kuhn 2 method, slightly better, it's decreasing, going to the set point for disturbance rejection. The Ziegler-Nichols method, roughly the same overshoot, but look like slightly faster going back to the response than the Cohen-Kuhn 2, but very close in terms of response behavior for Cohen-Kuhn 2 and Ziegler-Nichols, but not Cohen-Kuhn 1, a bit off, way off. And if you the other three methods, the ITAE, ISE, IE method, you can see them. The ISE method gives lower overshoot, ITAE method gives higher overshoot, but at the end of the day, all of them damp down, going to the final value offset 0, because it's the PI controller. But how it goes to the offset 0, different ways. The ISE less, you can see less overshoot, but a little bit more oscillation. Go down. The IAE, which is the black one, okay, higher overshoot, but slightly lower oscillation further on, maybe just and better decay. ITE high overshoot, again quickly decay and going down to the. So it's again it's not something fixed that we can decide which is the best method. You have to use different criteria to analyze to see which one is best or which one is suitable for your case But for this case, which one is the best tuning to use for this case, which is the best tuning. So all different tunings, you can see different values, set of values, and so on. This is something that what you have to do in your project and in the other presentation on using Simulink. That's what you can all do it all in Simulink. This sort of different comparisons, and it's up to you to decide. There's no one answer to one question, to one system, which is the best values. You have to make a good choice, good conclusion, analyze which is best for your case, and all of them can be accepted. Except if it's not stable, then we cannot choose that. But if it's stable, we can decide on which criteria is best for us to accept. So those are the different types of tunings that you see and the criteria. So it's, as I said before, it's related. You can use the tunings and then check the performance criteria, or can yet use the performance criteria to get the tunings and compare them. As I say, in simulation, you can use all these and compare. It's very easy. Manually, of course, you may have to choose one or two methods and then decide which one you want to use. To do it manually or to do it in online, the real system, and so on. Okay, so this is final part. Okay, you see again here all the same values as mentioned just now. This is question for you to answer, and we hope to get your answers on the WhatsApp after the class. Basically, why offset steady state criteria alone is not sufficient to decide the performance. You cannot just use offset to decide your performance. Why? Second question, what does decay ratio criteria show about the performance? Decay ratio shows what? Tells you what from the performance? We calculate decay ratio. Okay. Third one, why do we take squared? Why do we squared or take the absolute value of error for the dynamic criteria? All of them has got the ISC is squared, the IE is absolute value, not the actual error. Okay, the fourth question, what are the other dynamic criteria? In the notes, we mentioned only rise time, overshoot, decay. What others you can use for the dynamic criteria at certain time? Two types of dynamic criteria. For the first one, what other dynamic criteria you can use for that? Compare the different performance. Okay, the fifth one is for the ultimate gain, KU. What is the response? And in terms of the roots of equation, where does the root lies? Okay, and then for the next one, how many tuning methods did we mention in this class? What are they? And finally, which method gives the best response for the example just now? From your understanding, from your observation, which method gives the best response for the example? So hopefully you can answer this in the WhatsApp. Possible, yeah, we like different people to answer, and we can discuss in the WhatsApp for today, or maybe and again go to it next week. We will further on discuss on this methods. Okay, thank you very much. Up to this point, we'll stop, and then we will discuss the lecture, discuss the questions, and we'll have any more questions on the project, you can ask me on the WhatsApp discussion. Thank you very much.